What is life? Is it something that breathes, that moves, that simply exists? Or is it something far more elusive? If a strange microbe were staring at us from a Martian rock, would we even know it was alive? And if life thrived in the oceans beneath Europa's icy shell, or floated in Titan's methane skies, would we recognize it when we saw it? Close your eyes and imagine a tiny rock lying in the frozen silence of Antarctica, just another stone half buried in the windswept snowdrifts of Allen Hills. But this one came from another world. Roberta Score, a lab manager from NASA's Johnson Space Center, was out there in the white void when she found it. At first glance, it looked like any other meteorite, but when scientists brought it home, examined its chemistry, and matched its fingerprint to the Martian surface, it revealed its true origin, Mars. And inside this unassuming piece of ancient basalt, something even more profound, chain-like microscopic structures uncovered through electron microscopy features that resembled fossilized organisms on Earth. Had we perhaps discovered the first whisper of life beyond Earth, locked in stone and time? This single rock, ALH 84001, launched a storm of debate, speculation, and wonder. Scientists scrutinized every micron, every chemical clue. Were these structures evidence of Martian biology, or just geology playing tricks with our expectations? But the rock posed a deeper question, one still unanswered. If life is out there, would we even recognize it? To search for life in the cosmos, we must first ask what life truly is. How do we define it without knowing what it might look like elsewhere? What are the universal signatures of life, if such signatures even exist? Could life be simple, hidden in dust or ocean spray? Or could it be something far stranger than anything we've imagined? In this journey, we'll explore how scientists define life not just as something that eats or moves or reproduces, but as a self-organizing information-storing system capable of reaction, replication, and adaptation. We'll venture from the chemistry of DNA to the lost seas of early Mars, from the cryogenic lakes of Titan to the boiling vents of Europa's abyss, asking again and again, is this where life begins? In December 1984, a small rock resting on the ice fields of Antarctica was picked up by Roberta Score, a field manager from NASA's Johnson Space Center. To the untrained eye, it was an unremarkable find. But ALH 84001, as it was cataloged, would soon become one of the most controversial meteorites in history. Initially identified as a meteorite, its chemical composition later revealed something far more astonishing. It originated from Mars. This Martian exile had been launched into space millions of years earlier by a powerful impact event and had journeyed silently through the solar system before crashing into Earth and resting undisturbed in the icy plains. After its retrieval, scientists conducted intensive studies, and nearly a decade later, a team led by physicist David S. McKay made a startling announcement. Under electron microscopy, they observed chain-like microstructures embedded within the rock features they argued could not be explained by abiotic chemistry alone. These, they proposed, were fossilized remains of Martian microorganisms. The world took notice. NASA's announcement made global headlines. Even President Bill Clinton addressed the nation, framing the discovery as a potential turning point in human understanding of life in the universe. But as the excitement cooled, scrutiny intensified. Other scientists pointed out that such microstructures could be formed by purely chemical processes without any biological involvement. The claim that ALH 84001 harbored Martian life began to fracture under the weight of peer review and alternative explanations. Yet even amid doubt, ALH 84001 continues to serve as a profound reminder of a deeper question. Even if alien life stood before us, would we be able to recognize it? The challenge of identifying extraterrestrial life begins with the challenge of defining life itself. To date, scientific literature offers over 200 definitions, but most of these can be distilled into a core framework grounded in three essential characteristics. First, life must possess the ability to store information. This means encoding details about its internal state structure and function in a stable medium. Second, life must catalyze chemical reactions. It must interact with and respond to its environment, acquiring energy, building complexity, and adapting to changes. Third, life must be able to replicate, producing copies of itself that preserve its structure and functions across generations. The renowned physicist Erwin Schrödinger was among the first to articulate these principles from a physical perspective. He understood that the transmission and preservation of information lay at the heart of life's persistence. From information comes reaction, and from reaction comes replication. These processes together enable what we observe as living systems that move, metabolize, respond, evolve, and above all endure. A more concise but profound definition was proposed later. Life is that which undergoes Darwinian evolution. It is the capacity for change through selective pressure and inherited variation that allows life to adapt and thrive across a range of conditions. On Earth, we see this manifest in all known biological systems. Our own biochemistry hinges on DNA for information storage, RNA for information transfer, and proteins as functional catalysts. DNA stores our genetic code. RNA interprets that code, and proteins carry out the essential reactions of metabolism and structure building. Importantly, these molecules participate in feedback loops. DNA can instruct the creation of proteins that replicate DNA itself. This elegant cycle is the molecular heart of terrestrial life. But when we seek life beyond Earth, we are faced with the daunting question, must alien life mirror this same molecular choreography? If not, how will we recognize it? Even within Earth's biosphere, we encounter ambiguous cases. Take viruses, for instance. They contain genetic material and reproduce, but only within a host. They catalyze reactions, but only passively. Are they truly alive? Then there is abiogenesis, the emergence of life from non-life. At some point on early Earth, chemistry gave way to biology, yet the boundary between the two is neither sharp nor well understood. It is highly likely that early life lacked the full DNA, RNA, protein triad. One leading hypothesis suggests that RNA alone may have been the first self-replicating molecule, giving rise to the so-called RNA world. Such primitive systems would be almost unrecognizable to us today, and yet they would meet the minimal criteria for life. They would evolve, they would interact, they would replicate. To better understand what extraterrestrial life might look like, we must consider the physical and chemical environments in which life is likely to emerge. Solvents are a critical piece of this puzzle. Life, as we know it, relies on a solvent to host biochemical reactions, dissolve nutrients, and mediate transport. On Earth, that solvent is liquid water. Water has several remarkable properties. It is chemically stable, capable of forming hydrogen bonds, effective at dissolving a wide range of compounds, and maintains its liquid state over a broad temperature range. Early life on Earth almost certainly relied on liquid water, and perhaps more importantly on moderate temperatures that allowed water to remain in its liquid state. Though extremophiles exist, organisms that thrive in boiling vents or acidic lakes, the origins of life likely occurred in more temperate, chemically stable environments. Moreover, early life utilized the same elemental building blocks that persist today: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon, in particular, is a superstar of molecular versatility, capable of forming stable and complex molecular structures essential for information storage and catalysis. The upshot is that early life on Earth, while primitive, was not entirely alien to us. It emerged under familiar conditions using familiar chemistry. Thus, it is reasonable, though not guaranteed, to hypothesize that life elsewhere in the universe may follow similar patterns. This hypothesis brings us back to Mars. Billions of years ago, Mars had liquid water on its surface, a thicker atmosphere, and a temperate climate. If life ever began there, it might have been carbon-based, water-dependent, and similar enough to Earth life for us to detect. And this is what made ALH 84001 so compelling. It could have been a glimpse into an ancient shared biological heritage. However, beyond Mars, the story grows more exotic. The icy moons of the outer solar system offer new and alien laboratories in which life might exist. Europa and Enceladus both harbor subsurface oceans beneath thick crusts of ice. These oceans are kept liquid not by sunlight, but by tidal heating from their host planets. Here in total darkness, life might rely not on photosynthesis, but on chemosynthesis, drawing energy from the heat and chemicals emitted by hydrothermal vents. Could microbial life thrive in these subsurface oceans, feeding on dissolved nutrients? Could evolution produce more complex organisms, perhaps eyeless creatures navigating by touch and echo, suspended in an alien sea? Titan, Saturn's largest moon, presents an even more bizarre possibility. Its frigid surface is dotted with lakes and rivers, not of water, but of liquid methane and ethane. At 180 degrees Celsius, water is as hard as rock. But methane is fluid and could, in theory, act as a solvent for a radically different form of life. Could chemical reactions proceed in such an environment? Could life emerge with membranes, metabolism, and replication, but without the warm, aqueous chemistry of Earth? The search for life in such places pushes our definitions to their limits, but even more extreme possibilities beckon. Might life exist that is silicon-based instead of carbon-based? Might it use ammonia, sulfuric acid, or even supercritical carbon dioxide as a solvent? Could quantum systems or unknown forms of matter support a form of existence that fulfills the criteria of life without resembling anything we currently understand? These possibilities remain speculative. Our only confirmed example of life is terrestrial. But as we begin to explore these questions, our first step must be disciplined. We must begin with what we know. Thus, in the search for the earliest life in the universe, we ground ourselves in the strictest definition. Life that uses water as a solvent exists within a reasonable thermal range and is based on carbon and its associated biochemistry. This definition serves as a foundation. It is the model by which we design instruments, craft experiments, and interpret data. From Mars rovers to Europa landers, from Titan probes to telescopes peering into exoplanet atmospheres, we begin by searching for the familiar. And with time, if we are fortunate, we may one day uncover the unfamiliar. But even then, we will ask, does it store information? Does it catalyze reactions? Does it replicate? If the answer is yes, we may finally say we are not alone. How to make life from cosmic dust to conscious beings. In the spring of 1952, in a laboratory at the University of Chicago, graduate student Stanley Miller initiated an experiment that would mark a watershed moment in the scientific search for life's origins. Working under the guidance of Nobel laureate Harold Urey Miller, designed a deceptively simple apparatus to simulate the atmospheric conditions of the early Earth. Into a sealed flask, he placed water to represent ancient oceans and filled the remaining volume with a gas mixture composed of methane, ammonia, and hydrogen molecules presumed abundant on the prebiotic planet. A continuous electrical spark arced through the chamber, standing in for the lightning strikes that would have been common in Earth's volatile primordial skies. At first, nothing seemed to happen. But after a few days, the water took on a faint pink hue. After a week, the mixture had turned a deep crimson. When Miller analyzed the contents using paper chromatography, he discovered something extraordinary. The liquid contained a suite of organic compounds, specifically amino acids, the very building blocks of proteins and by extension of life. Miller's experiment delivered a powerful message to the scientific community under the right conditions. Simple inorganic molecules can spontaneously give rise to the precursors of living systems: glycine, alanine, aspartic acid. These were not mere curiosities. They were biochemical fundamentals synthesized from scratch in a glass vessel with nothing more than water, common gases, and a source of energy. The implication was profound. If the chemistry of life could emerge in a lab, perhaps it had also emerged in the ancient pools of a young Earth. What made the experiment even more compelling was its elemental simplicity. The gases used, methane, ammonia, and hydrogen, are among the most common in the universe, composed of the basic building blocks of matter: carbon, hydrogen, nitrogen, and oxygen. These molecules are widespread throughout planetary atmospheres, comets, and interstellar clouds. That such ordinary constituents could yield such complex outputs hinted at a remarkable possibility. Life might not be a singular fluke of Earth, but a natural consequence of universal chemistry. Subsequent analysis of the original experiment's sealed vials revealed that Miller had synthesized even more amino acids than he initially detected, including some not commonly used in terrestrial biology. This raised another tantalizing prospect. The biochemistry of Earth may represent just one solution among many. Life constrained by evolutionary path dependence had settled on 20 primary amino acids, but chemically the potential permutations are far more diverse. The Miller-Urey experiment illuminated a key step in the transition from chemistry to biology, but it was only one piece in a much larger puzzle. To trace the origin of life, we must identify where the right ingredients, environmental conditions, and timescales converge. This raises the central question: where else in the universe could such a recipe be fulfilled? The Earth, of course, is our only confirmed data point. Our planet is awash in liquid water, bathed in sunlight, and shielded by a thick but balanced atmosphere. Critically, Earth orbits within the so-called habitable zone of the Sun, a circumstellar region where temperatures are suitable for liquid water to exist on a planet's surface. Move closer to the star and water vaporizes. Move farther away and it freezes. For life as we know it, liquid water is non-negotiable. Every star possesses its own habitable zone, the location of which depends on the star's mass and luminosity. For smaller stars, the zone is compact and hugs the star tightly. For massive luminous stars, the zone stretches far into space. In our solar system, the habitable zone stretches from just inside the orbit of Venus to just beyond that of Mars. Yet only Earth hosts persistent surface water today. Venus once, perhaps Earth-like, underwent a runaway greenhouse effect. The increasing luminosity of the aging sun triggered the evaporation of its oceans, loading the atmosphere with water vapor and driving up surface temperatures. The result was catastrophic: an atmosphere choked with carbon dioxide and a surface hot enough to melt lead. Mars, conversely, suffered a slower fate. Geological evidence indicates that Mars once had a thicker atmosphere and flowing water rivers, lakes, and perhaps even oceans, but the planet's small size sealed its doom, with a weak gravitational grip and a rapidly cooling core. Mars lost its magnetic field early in its history. Without this shield, the solar wind stripped away its atmosphere, and the water eventually froze or sublimated Mars, dried out, and fell silent. These cautionary tales underscore how delicate the balance is. Being in the habitable zone is not sufficient. Planetary mass magnetic fields, geological activity, and atmospheric composition all play decisive roles. Even galaxies have habitable zones. Too close to the galactic center, and radiation from supernovae sterilizes everything. Too far out, and heavy elements become scarce, hindering planet formation. But even in the most promising environments within a star's habitable zone, on a geologically active world, with water life cannot arise without the essential ingredients organic molecules. This returns us to the question of where those molecules originate. Earth may have begun with water, but not all of it was available at the surface. Much of the early water became chemically bound in the planet's interior or was lost during its molten phase. One prevailing theory holds that water and organics were delivered via impacts from icy comets and carbonaceous asteroids. These celestial messengers formed in the cold outer regions of the solar system retained volatile compounds and organics, which they deposited on young Earth during the so-called late heavy bombardment. This idea gained powerful support in 2014 with Japan's Hayabusa 2 mission to the asteroid Ryugu. The spacecraft retrieved dust samples and returned them to Earth. Laboratory analysis revealed a host of organic molecules, including several amino acids. These compounds had survived for over 45 billion years in deep space, shielded from harsh radiation. Their presence implies that the chemistry necessary for life was seeded across the solar system long before Earth's oceans even formed. Other lines of evidence reach further still. In 2003, astronomers detected glycine, the simplest amino acid in giant molecular clouds. These vast reservoirs of gas and dust are the birthplaces of stars and planetary systems. Spectral signatures of complex organics have been identified not only in our galaxy, but in others, even in the light of distant quasars. These findings suggest that the molecular precursors of life are not just widespread, but ancient. The cosmos was cooking organics long before our sun ever shone. The origin of these molecules, in turn, is rooted in the life cycles of stars. The periodic table is a stellar artifact. In 1957, astrophysicists Margaret and Jeffrey Burbidge, William Fowler, and Fred Hoyle published a landmark paper describing stellar nucleosynthesis. Stars, through nuclear fusion, forge elements from hydrogen. Our sun is currently fusing hydrogen into helium. Larger stars go further, fusing helium into carbon, oxygen, nitrogen, and beyond up to iron. When massive stars reach the end of their lives, they explode as supernovae, scattering their enriched cores into space. These explosions also forge heavier elements like nickel and cobalt. But the heaviest elements, gold, platinum, uranium, require even more extreme conditions. It is now understood that the collision of neutron stars with their immense gravitational and nuclear densities can generate the perfect environment to produce these rare elements. The universe, in other words, must be thoroughly recycled by successive generations of stars before life can begin. The Big Bang produced only hydrogen, helium, and traces of lithium. It was not until the first stars formed hundreds of millions of years later that heavier elements began to appear. Life in any form must therefore wait for at least one generation of stars to live and die. Planets rich in carbon, nitrogen, oxygen, and phosphorus only emerge after stellar alchemy has run its course. And only then, in the presence of water and suitable environmental conditions, can amino acids, sugars, and lipids begin to form. Life as we know it is not only rare in its complexity, it is rare in its preconditions. It depends on billions of years of astrophysical preparation, a precise orchestration of heat chemistry, timing, and stability. It is a story not just of biochemistry, but of cosmochemistry, of stars, planets, comets, clouds, and collisions. The Miller-Urey experiment demonstrated the plausibility of this alchemy under the right conditions, but the cosmic laboratory is vaster and older than any earthbound flask. To find the earliest possible emergence of life, we must therefore look not just to Earth-like planets in habitable zones, but also to the distribution of the raw ingredients, organic compounds, water, and heavy elements. We must track the chemistry of the universe backward through time, through stellar generations, through galactic cycles, all the way to the first molecules that ever formed. And eventually, to reach the ultimate origin, we must peer into the era before the first stars were born, into the dark ages of the universe when only hydrogen and helium drifted silently through the void, awaiting their moment to ignite and begin the long transformation from light to life. The earliest possible life. Let us imagine a future moment when humanity finally cracks one of the greatest mysteries of the cosmos. After decades of relentless investigation, theoretical models, experimental efforts, and technological innovation, the elusive identity of dark matter is revealed, not through myth or metaphor, but through the clean, precise lens of particle physics. A single stable particle, previously unknown, emerges as the solution. It interacts only gravitationally and occasionally through the weak nuclear force. The standard model of physics is updated detectors confirm its presence, and laboratories that once buzzed with dark matter pursuits fall quiet. The intellectual fire dims, proposals dry up, and the world of physics turns its focus elsewhere. But not everyone moves on. A quiet circle of researchers, driven not by consensus but by anomaly, remains unsatisfied. There is still a persistent signal, an excess of gamma-ray radiation flowing from the center of the Milky Way. For decades, it was dismissed as noise or as a byproduct of mundane interactions. But now, with the dark matter particle confirmed, the anomaly lingers unexplained. Driven by curiosity and the allure of unfinished business, these scientists pool what little funding they can, building a high-resolution gamma-ray telescope aimed squarely at the heart of our galaxy. And there it is, the expected glow of dark matter annihilation, predictable, consistent. Except for one detail, the signal is not steady. Subtle, almost imperceptible fluctuations emerge. The signal breathes. Minute changes in intensity repeat with maddening irregularity. The team works tirelessly, formulating and discarding theory after theory. Eventually, the funding expires. Disillusioned, the group disbands. Yet one researcher, a former graduate student, cannot let it go. On a restless night, she reopens the archived data and looks again. A new filter, a new method, a fresh eye, and then something unmistakable. A rhythmic pattern hidden in the noise. Every few seconds, the gamma ray intensity shifts up, then down, precisely like a binary signal. It continues, repeats, pauses, then resumes again after a month. And suddenly she begins to write, marking each increase as a 1, each decrease as a 0. The question is no longer about dark matter alone. It becomes something infinitely greater as the universe speaking. To answer such a question, we must first ask, what is life? What is its minimum requirement, and when could it have first emerged? Traditionally, life is defined as a system that can store information, interact with its environment, and most importantly, replicate itself. These are the foundational pillars of Darwinian evolution. On Earth, this triad is fulfilled by the interplay of DNA, RNA proteins, and the dynamic chemistry of carbon-based molecules bathed in liquid water. But such a framework depends on a specific environment, a rocky planet orbiting a stable star with surface temperatures suitable for liquid water and access to a rich supply of elements like carbon, hydrogen, nitrogen, and phosphorus. When then could such a system first have arisen in the universe? We know that the universe began in a blaze of radiation and plasma nearly 138 billion years ago. For the first several 100,000 years, no atoms could form. The universe was too hot, too dense. Only after roughly 380,000 years did the cosmos cool enough for neutral hydrogen to emerge. But even then, there were no stars, no planets, only a featureless expanse of cooling gas and dark matter. The first star's massive short-lived beacons, composed only of hydrogen and helium, ignited perhaps 100 million years after the Big Bang. These early stars lived briefly, exploding in titanic supernovae that enriched their surroundings with heavier elements: carbon, oxygen, nitrogen, the chemical seeds of biology. And so began the cosmic cycle of stellar death and rebirth. With each generation, the interstellar medium became more chemically complex. It is only after several rounds of such recycling that enough raw material accumulated to allow for the formation of rocky planets. If the timeline holds, then the earliest plausible moment for Earth-like life to arise, life built on carbon driven by water and capable of Darwinian evolution, must have occurred somewhere between 100 and 500 million years after the universe's birth. The Earth itself came far later, forming around 46 billion years ago, which means the first life in the cosmos almost certainly predates our own planet. But this still reflects only the biochemistry that we know. What of the chemistry we have not yet imagined? Astrobiologists have long speculated on alternative biochemistries. Water with its polarity and thermal properties may be ideal for Earth life, but it is not the only conceivable solvent. Methane, ammonia, hydrogen sulfide, and even liquid hydrogen fluoride have been proposed. Phosphorus might be replaced by arsenic. Carbon might yield its role to silicon, which also forms long molecular chains. Each substitution brings constraints but also possibilities. In 2007, physicist Vadim Sidovich showed that dust grains in plasma could, under the right conditions, self-organize into complex spiral structures. These are not living things, but they hint that matter, even in the most minimal and non-biological forms, has an innate capacity for order. Yet even these exotic life forms depend on chemistry, and chemistry requires atoms, which in turn require stars. No matter how alien all forms of life conceived so far must await the forging of elements in stellar furnaces. If we seek to push the origin of life even earlier, we must look beyond conventional matter. Theoretical physicist Frank Drake once speculated that life could form in the interior crust of neutron stars. These objects, the ultra-dense remnants of massive stars, possess unique states of matter. Nuclear pasta that exist nowhere else in the universe. Here, atomic nuclei are crushed into bizarre shapes, held together by the strong nuclear force. In such an environment, structures might self-organize, interact, and replicate, driven by the star's intense heat. It is speculation, yes, but within the bounds of known physics. Others have proposed more abstract entities, magnetic monopoles, strung together by cosmic strings, forming networks capable of evolution. Yet the very existence of such particles remains unproven. And crucially, such exotic matter still requires energy and structure, conditions provided only by the emergence of stars. And so we arrive at the most radical possibility: life in the dark sector. Over 95% of the universe's mass energy content lies in the form of dark matter and dark energy entities that do not interact with light and remain for now invisible to our instruments. While dark matter is typically modeled as simple and inert, it is possible that it may host complex interactions of its own. There could be multiple species of dark matter particles governed by dark forces capable of forming dark atoms and dark molecules. If so, then a parallel form of chemistry utterly alien to us may exist in the shadows of the universe. If dark matter possesses structure, interactions, and internal energy, then it might also possess evolution. And if evolution is possible, then so too is life. Such life would not depend on stars. It might draw energy from interactions unknown to us. It might have emerged in the very first moments of the universe, long before the first photon of light escaped into the cosmic microwave background. It might still exist now, floating invisibly between galaxies, brushing past our detectors without ever triggering a signal. And perhaps, just perhaps, it is trying to communicate. Perhaps those gamma-ray signals dismissed as noise were structured emissions from intelligences forged in the dark. But such ideas remain speculative. To find the earliest possible life, we must return to what we can constrain. The universe did not produce the first stars until roughly 100 million years after the Big Bang. Only then could heavy elements begin to form. Only then could planetary systems, rocky surfaces, atmospheres, and oceans emerge. Even under the most generous conditions, life as we know it could not have arisen before this threshold. And even if more exotic forms of life emerged earlier, we may never have the means to detect them. The question then becomes not just when life first arose, but whether we will ever know that it did. Information from those ancient epochs is scarce. Time has stretched and faded the signals. The cosmos has expanded, and with it, the evidence has cooled and dimmed. If a civilization rose and fell billions of years before the Earth formed, leaving behind only faint traces encoded in gamma rays or gravitational waves, would we recognize them? Would we understand? Perhaps life began in the shadows, passed through fire, and emerged, blinking into the light. Or perhaps it danced in the dark, unseen and eternal, whispering across the void. The first life may not have looked like us, thought like us, or even existed in the matter we know, but life in all its possible forms has one thing in common: it leaves patterns. And if we are to find it, we must learn how to read them. Where is everybody? On a warm summer afternoon in 1950, the renowned physicist Enrico Fermi found himself immersed in a seemingly casual lunchtime conversation with colleagues at Los Alamos. The subject, as it often does among those who contemplate the fundamental nature of the universe, had drifted toward the prospect of extraterrestrial life. They speculated freely, throwing around ideas about the abundance of stars, the likelihood of Earth-like planets, the evolution of intelligent beings, and whether any of them might have visited us. The discussion moved on as conversations do, until Fermi, who had been silent for some time, abruptly posed a simple yet disarming question: where is everybody? This inquiry, deceptively innocent in tone, belied its profound implications. It is a question that has since reverberated through the decades as the central premise of what is now called the Fermi paradox, a contradiction between high probability and conspicuous absence. Given the vastness of the cosmos, the abundance of potentially habitable worlds, and the immensity of time available for life to arise, why have we seen no evidence of alien civilizations? The paradox challenges our assumptions about the prevalence of life, the evolution of intelligence, and the nature of cosmic communication. The chain of reasoning begins with Earth itself. Our planet is not special in any fundamental sense. It is a rocky world orbiting a main sequence star, bathing in the warmth of a stable energy source, replete with water, carbon-based molecules, and a relatively benign atmosphere. It possesses a dynamic geology, a magnetic field, and a thin yet protective layer of atmosphere factors that together allowed life to gain a foothold, and through the crucible of evolution eventually produce intelligence. But these features are not unique. In fact, our Milky Way galaxy contains an estimated 100 billion stars, and recent observations suggest that as many as 5 billion of them may host Earth-like planets within their habitable zones regions where temperatures permit liquid water to exist on the surface, and this is merely one galaxy among possibly 2 trillion others within the observable universe. Moreover, the principle of mediocrity in physics, the idea that the Earth does not occupy a privileged position, suggests that the conditions for life, while complex, are not unique to our planet. Nature rarely performs singular acts. If a phenomenon is allowed by the laws of physics, and if there is sufficient time and space for it to occur, then it is almost guaranteed to happen more than once. Life, by this logic, should be common. And given the age of the universe, 8 billion years, there has been ample time for life not only to emerge, but to evolve into intelligent forms, capable of technology and communication. Indeed, life on Earth appeared as soon as conditions allowed. Geological evidence places the first microbial life at roughly 38 billion years ago, shortly after the Earth's surface cooled and oceans formed. The process of abiogenesis, whereby inanimate matter gave rise to self-replicating chemical systems, was not instantaneous, but nor did it require billions of years. Life appears to have arisen with remarkable haste, given the planet's violent infancy. This swiftness implies that once the right ingredients are present, life is not only possible, but perhaps inevitable. If this is true elsewhere, then by now the galaxy should be teeming with civilizations. Many of them would have had hundreds of millions, even billions of years of head start on us. Even at modest technological rates, such civilizations could feasibly colonize an entire galaxy within a few million years, a blink in cosmological terms. With self-replicating probes, interstellar travel becomes not a fantasy, but an engineering problem. Civilizations could communicate across light years using radio or laser signals. Artifacts of their presence, whether intentional or accidental, should be detectable. The solar system ought to be littered with evidence, alien probes, megastructures, chemical anomalies, or encoded transmissions drifting in the radio sky. Yet we find nothing. No signals, no probes, no artifacts, no signs of alien technology past or present. Not even biosignatures in the atmospheres of distant exoplanets. This is the silence that Fermi found so perplexing. The sheer absence of evidence is not merely disappointing, it is statistically improbable under the assumption that life is common and intelligence a frequent byproduct. Several explanations have been proposed to resolve this dissonance. The first is perhaps the most sobering, that life itself is extraordinarily rare. The path from chemistry to biology may require a precise sequence of events and environmental parameters, so exacting that even among billions of planets, only a handful, perhaps only one, manage to navigate it successfully. Perhaps the emergence of life demands not only water and organics, but a confluence of tectonic activity, magnetic shielding, climatic stability, and countless other factors still poorly understood. If so, Earth may be a statistical outlier, a cosmic accident. Alternatively, life may be common but intelligence rare. Evolution does not favor complexity unless it provides a survival advantage. Microbial life dominates Earth's history and biomass. Intelligence, on the other hand, has arisen only once in 4 billion years. It is not clear that cognition of our kind is a convergent evolutionary strategy. Perhaps the development of tool-use language, abstract thought, and technological capability is the exception rather than the rule. Countless alien biospheres may thrive beneath alien suns, but their inhabitants may lack the desire or the capacity to contemplate the stars. Yet another possibility is that intelligence often arises but seldom endures. Civilizations may emerge, rise to brilliance, and then collapse. The threats are many. Ecological collapse, nuclear self-destruction, runaway artificial intelligence, pandemics, or perhaps even cosmic events like gamma-ray bursts. Technological sophistication may carry within it the seeds of extinction. If civilizations tend to destroy themselves before achieving interstellar reach, the galaxy may be a vast cemetery of dreams, worlds where intelligence once bloomed but left behind no lasting mark. It is also conceivable that we are simply not looking correctly. The methods we use to search listening for radio signals, scanning for atmospheric anomalies, hunting for Dyson spheres may be inadequate or misguided. Alien civilizations may use modes of communication or technology so advanced or so different from ours that we fail to recognize them. Just as an ant cannot comprehend a quantum computer, we may lack the sensory or intellectual apparatus to detect alien activity. Our assumptions may be anthropocentric, blinding us to more subtle or exotic indicators. Some have proposed that intelligent civilizations actively avoid contact, a concept known as the zoo hypothesis, suggesting that Earth is being deliberately shielded or ignored by a galactic community. Others speculate that we are alone, not because life is rare, but because we are the first cosmic pioneers in a young and expanding universe. If intelligence takes billions of years to emerge, perhaps humanity represents the beginning rather than the middle of a galactic story. Meanwhile, searches continue. SETI, the search for extraterrestrial intelligence, scours the sky for radio signals with artificial fingerprints. Infrared telescopes hunt for signs of waste heat from alien megastructures. Spectroscopic studies of exoplanet atmospheres look for biosignatures, gases like oxygen, methane, or ozone that cannot be explained by geology alone. Missions to Mars. Europa, Enceladus, and Titan seek microbial life beneath the ice in salty plumes or hydrocarbon lakes. Every discovery sharpens our understanding, but the silence remains. Still, the paradox endures. The more we learn about the universe, the more likely it seems that life should exist beyond Earth. Yet, with each failed search, the mystery deepens. Perhaps in time we will find that the cosmos teems with life and that our isolation is only temporary. Or perhaps we will confirm that we are truly alone, an extraordinary exception in an otherwise lifeless void. But if we are alone, then the implications are profound. It would mean that intelligence is not merely rare, it is sacred, that our responsibility as the sole conscious observers of the cosmos is immense. We would be the keepers of memory, the only eyes through which the universe contemplates itself. And if we are not alone, if someday we detect a faint signal, intercept a relic probe, or decode a message carved into the stars, then the paradox will finally yield. We will no longer ask, "Where is everybody?" but instead, what will we say to them? Perhaps one day, far in the future, our descendants will voyage among the stars and uncover the tombs of ancient civilizations, dead worlds, derelict machines, forgotten archives, whispering tales of triumph and tragedy. Perhaps they will discover that we were not the first nor the last to ask the question, that others too once looked to the sky and wondered. That in the dark, somewhere beyond the light of our sun, a monument still waits to be found. A distant Göbekli Tepe of alien origin left behind by minds that once dreamed. And in that discovery, we may find not just answers about others, but something essential about ourselves.
What if the ancient myths were more than just stories? What if, in their poetic descriptions of sun gods and celestial origins, they captured an essential truth about our existence? Could it be that, in some fundamental way, the sun truly is our God, not as a supernatural entity, but as the very source of our being? On the most basic level, the sun's radiant energy sustains life on Earth. Its warmth maintains temperatures within the critical range that allows liquid water to exist, creating the conditions necessary for biological processes. Photosynthetic organisms capture sunlight and convert it into chemical energy, fueling the intricate web of life. Every breath we take, Every movement we make is ultimately powered by solar energy transformed through countless biological interactions. Without the sun, Earth would be an icy, lifeless world adrift in the void. Yet, our connection to the sun runs even deeper. We are not merely recipients of its energy, we are, quite literally, built from the remnants of its cosmic ancestors. Just as ancient myths speak of sun deities born from primordial forces, our sun itself is a descendant of earlier stars. It was not the first of its kind, but a member of a long lineage of celestial bodies that have continuously shaped the universe. The sun emerged from a stellar nursery, a dense cloud of gas and dust pulled together by gravity. As matter accumulated, it compressed and heated until nuclear fusion ignited in its core, giving birth to the luminous sphere we see today. But where did this vast nebula come from? The answer lies in the life cycles of stars that came before. Our sun is classified as a population 1 star, meaning it was formed from the enriched remnants of older, now long extinct stars. These ancestors, population 2 stars, transformed the primordial hydrogen and helium of the early universe into heavier elements through nuclear fusion. In their final cataclysmic deaths as supernovae, they scattered these elements across space, seeding the next generation of stars. But even these were not the first stellar architects. Theoretical models predict the existence of an even earlier generation, the elusive population 3 stars, the first to ignite after the Big Bang. These stars, composed purely of hydrogen and helium, were colossal and short-lived, burning with an intensity that rapidly fused lighter elements into the building blocks of future celestial bodies. Though never observed directly, their fingerprints remain in the chemistry of ancient stars and the cosmic background radiation. Thus, our sun is the product of an ongoing cosmic cycle, a vast and intricate process of creation, destruction, and rebirth that has unfolded over billions of years. The elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were all forged in the hearts of stars long before our solar system even existed. Perhaps then the ancients were onto something. The sun is not just the center of our solar system, but a testament to the universe's grand design. It is the latest in an unbroken chain of cosmic fire, linking us to the very origins of matter itself. And so, in a way, the sun truly is our God, not in the form of myth, but as the ultimate source of life, energy, and existence itself. The alchemist's dream, from ancient transmutation to modern nuclear science. The year was 1782. In the hallowed halls of Great Britain's Royal Society, a claim emerged, one so audacious that, if true, it would resolve one of humanity's most enduring mysteries. A young and ambitious chemist, James Price, asserted that he had unlocked the secrets of transmutation, the fabled transformation of base metals into gold. Unlike the common charlatans who thrived on deception, Price presented empirical evidence, bolstered by experiments conducted before witnesses. His method, he claimed, involved the use of 2 mystical powders, a white powder that could turn mercury into silver and a red powder that could convert it into gold, producing an astonishing 60-fold increase in mass. While many of his contemporaries remained skeptical, his achievements did not go unnoticed. The University of Oxford conferred upon him an honorary medical degree, not explicitly for his experiments, yet the timing suggested a connection. To the public, it seemed that Price had finally proven alchemy to be a science rather than a fantasy. However, when the Royal Society pressed for a demonstration under its direct supervision, Price hesitated. He argued that the synthesis of these powders was so physically and financially exhausting that it rendered the entire process impractical. He insisted that his reputation as an honorable scientist should suffice to validate his findings. But in the face of mounting scrutiny, he relented. In January of 1783, Price stood before his esteemed peers, prepared to replicate his miracle. Yet, rather than performing alchemy, he consumed a vial of laurel water, rich in cyanide, and perished before their eyes. With his death, his secrets were lost, and his claim was cast into the realm of myth. Yet the desire to transmute elements did not die with James Price. It merely transformed. The dream of alchemy persisted, its spirit reborn in the crucible of modern physics. It was no longer gold that scientists sought, but a deeper understanding of matter itself. This quest would find its champion in a man who would revolutionize science, Ernest Rutherford. Born in 1871 in New Zealand, a remote British colony, Rutherford's brilliance propelled him from a single-room schoolhouse in Havelock to the hallowed halls of the University of Cambridge. At the turn of the 20th century, radioactivity was a nascent field, and Rutherford was among its earliest explorers. In his laboratory at McGill University in Canada, he and his colleague, Frederick Soddy, made a startling observation. Thorium, a heavy element, was spontaneously decaying into radium, a different element altogether. The implications were staggering. Soddy, in his excitement, proclaimed that they had discovered the secret of transmutation, the very goal of the ancient alchemists. But Rutherford, ever wary of the stigma attached to pseudoscience, cautioned him. For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists. Despite Rutherford's reluctance to embrace the language of the alchemists, their work marked a profound shift in scientific understanding. They had discovered that elements were not immutable. They could change, albeit not through magical powders, but through the hidden forces within the atom. By the 1920s, Rutherford had proven that elements could be intentionally altered. He demonstrated that by bombarding nitrogen atoms with alpha particles, energetic helium nuclei, he could produce hydrogen, an entirely different element. The experiment was further refined by Patrick Blackett, Rutherford's student, who used a cloud chamber to capture the moment of nuclear transformation. The photographic evidence left no doubt. Nitrogen had become oxygen. Blackett's work earned him the Nobel Prize in Physics in 1948, but the true revolution had already begun. Rutherford himself acknowledged the implications, remarking, "It is now possible by modern methods to produce exceedingly minute quantities of gold, but only by the transmutation of an even more costly element, platinum." Though his statement carried a touch of irony, it underscored a fundamental truth. Transmutation was real, but it was not economically viable. This newfound understanding of atomic structure would give rise to the most transformative scientific advancements of the 20th century. No longer were elements defined solely by their mass, as the ancients believed. Instead, the defining property of an element was its proton count, the number of positively charged particles in its nucleus. Change that number, and you change the element itself. Transmutation, therefore, could be achieved through several means. The first was through natural radioactive decay, in which an unstable nucleus emitted particles, thereby transforming into a lighter element. The second was through nuclear fission, in which a large atom, such as uranium, was split apart, a process harnessed for energy production and weaponry. The third was through nuclear fusion, the very process that powers the sun, wherein two smaller atomic nuclei merged to form a heavier element. Of these, fusion remained the most elusive and tantalizing goal. Nuclear fusion is the key to understanding the sun's extraordinary power. At its core, the sun fuses hydrogen atoms into helium, releasing an immense amount of energy in the process. This process is governed by two competing forces: the electrostatic repulsion between positively charged atomic nuclei and the strong nuclear force that binds them together. The strong force, though immensely powerful, operates only at extremely short distances. Overcoming the natural repulsion between atomic nuclei requires conditions so extreme that they are scarcely imaginable. Within the sun, where gravity exerts an unrelenting inward pull, fusion occurs at a relatively modest temperature of 15 million degrees Celsius. But on Earth, absent the sun's immense gravitational compression, scientists must generate temperatures exceeding 150 million degrees, 10 times hotter than the core of the sun, to force nuclei close enough for fusion to take place. The allure of fusion lies in its promise. Unlike fission, which produces long-lived radioactive waste, Fusion generates immense energy with minimal byproducts. Its fuel, hydrogen isotopes such as deuterium and tritium, is abundant, extracted from water and lithium. If harnessed successfully, fusion could provide a virtually limitless, clean energy source. Yet, despite a century of research, controlled nuclear fusion remains just beyond our grasp. The technical challenges are monumental. Plasma, the high-energy state of matter required for fusion, must be confined and stabilized within a reactor. The most promising approach, magnetic confinement, relies on powerful electromagnetic fields to trap plasma within a toroidal chamber, such as those found in tokamak reactors. Another method, inertial confinement, involves compressing tiny fuel pellets with intense laser beams to induce fusion. Both techniques have yielded progress, yet neither has achieved sustained, net positive energy output. Still, the pursuit continues. In laboratories across the world, scientists refine their methods, inching ever closer to the dream of practical fusion energy. Projects such as the International Thermonuclear Experimental Reactor in France and the National Ignition Facility in the United States stand as testaments to human ingenuity and perseverance. The journey from alchemy to nuclear science is one of the most remarkable sagas in human history. What began as a mystical quest for gold evolved into a profound exploration of the fundamental nature of matter. Today, transmutation is no longer the work of alchemists, but of nuclear physicists. We can transform elements not through arcane rituals, but through our mastery of atomic forces. The ultimate triumph, however, lies ahead. The quest to harness the power of the stars continues, driven by the same relentless curiosity that once inspired the alchemists. As we stand on the brink of a new energy revolution, we are reminded of an age-old question posed by the great physicist Arthur Eddington. What is the source of the heat which the sun and stars are continually squandering? Fusion, the cosmic fire and humanity's pursuit of the stars. In the early 20th century, at the annual meeting of the British Association for the Advancement of Science in Cardiff, the English astronomer and physicist Arthur Eddington posed a deceptively simple yet profound question to his colleagues. What powers the sun? At the time, the prevailing wisdom among scientists attributed the sun's radiance to gravitational contraction, a theory holding that as the sun's immense gaseous mass collapsed under its own gravity, the compression generated heat, much as the young Earth had done when it first coalesced from cosmic debris. While this theory explained the immediate source of solar heat, it bore an inherent contradiction. By the early 20th century, geologists and physicists had established that the Earth, and by extension the solar system, was billions of years old. However, calculations showed that if the sun's energy derived solely from gravitational collapse, it would have burned out in a mere 20 million years. The theory, Eddington contended, was not merely outdated, it was a corpse that had yet to be buried. Seeking a new answer, Eddington turned to the emerging field of nuclear physics, pioneered by his contemporary, Ernest Rutherford. He theorized that the sun must be tapping into an unknown and vast reservoir of energy, an energy source that could only be subatomic in nature. He proposed that deep within the sun, hydrogen atoms were fusing into helium, releasing an extraordinary amount of energy in the process. More than just explaining stellar luminosity, Eddington's insight laid the foundation for modern astrophysics, revealing that stars were not merely celestial lamps, but cosmic forges responsible for creating the elements that constitute our universe. Eddington estimated that this nuclear process could sustain the sun for 15 billion years, a figure slightly high by modern standards, but conceptually correct. His work did not just provide an answer to the riddle of stellar power. It ignited a new question: could humanity harness the power of the stars? Over the past century, scientists have pursued that question with fervor, recognizing that nuclear fusion represents a potential key to an abundant, clean, and near-limitless energy source. Yet, as history has often shown, the mastery of such forces holds both the potential for prosperity and the peril of destruction. The lesson of the brown dwarfs, an alternative path to fusion. While our sun and other true stars achieve fusion through the intense pressures of their immense gravitational fields, they are not the only objects in the cosmos capable of nuclear reactions. Brown dwarfs, celestial bodies that exist in the liminal space between massive gas giants and the smallest stars, offer a compelling lesson in alternative fusion pathways. Too small to sustain the fusion of ordinary hydrogen, brown dwarfs instead undergo a different kind of nuclear reaction, one that relies on an isotope of hydrogen known as deuterium. Unlike protium, which consists of a single proton, deuterium possesses an additional neutron bound to the proton by the strong nuclear force. This extra neutron reduces the energy barrier required for fusion, allowing brown dwarfs to generate heat despite their lower mass. Deuterium is relatively abundant in Earth's oceans, where 1 in every 5,000 hydrogen atoms is a deuterium isotope. In contrast, in Jupiter's atmosphere, this ratio drops to 1 in 40,000, a figure closer to the natural cosmic abundance of deuterium. This property of deuterium, that it requires less energy to fuse than protium, has drawn the attention of scientists seeking to recreate stellar processes on Earth. If nuclear fusion is to become a viable energy source, humanity must find a way to exploit this unique isotope's potential. The National Ignition Facility, humanity's first glimpse at controlled fusion. One of the most ambitious attempts to achieve nuclear fusion on Earth has come from the National Ignition Facility in California. Here, scientists employ a novel technique to recreate the conditions necessary for fusion by targeting a tiny fuel capsule with an array of 192 ultraviolet lasers. The capsule, composed of synthetic diamond and cooled to temperatures just above absolute zero, is placed inside a golden cylinder no larger than a pencil eraser. In an instant, the lasers deliver an immense pulse of energy, causing the capsule to implode. This implosion generates the extreme temperatures and pressures necessary to trigger fusion, mimicking the energy dynamics found in brown dwarfs. At the heart of NIF's experiments lies the fusion of deuterium with tritium, a third isotope of hydrogen that contains 2 neutrons in its nucleus. When deuterium and tritium combine, they yield helium-4, the most abundant isotope of helium, and release an unbound neutron carrying 80% of the reaction's energy. In August 2021, NEF achieved a historic milestone. A single experiment fused approximately 200 micrograms of deuterium and tritium, momentarily generating a staggering 10 quadrillion watts of power, nearly 700 times the output of the entire United States electrical grid. However, this burst of energy lasted only 100 trillionths of a second and produced a net output sufficient to power a light bulb for just 6 hours. More importantly, the reaction reached 70% energy efficiency, edging ever closer to the long-sought goal of break-even, where energy output surpasses energy input. Despite this progress, 2 fundamental challenges remain. First, fusion reactions must generate more usable energy than they consume. Second, they must be sustained long enough to be practical for power generation. While NIF's method has shown promise, scientists continue to search for alternative approaches that can yield self-sustaining fusion reactions. The most ambitious project in the quest for nuclear fusion is the International Thermonuclear Experimental Reactor in France. Slated for activation in late 2025, ITER aims to be the first facility to produce net positive energy through fusion. The team behind ITER hopes to generate 10 times the energy input, demonstrating that fusion can be a viable power source. However, even if successful, ITER's energy output will not be captured for use. It will serve purely as an experimental proof of concept. Beyond deuterium-tritium fusion, alternative fuels such as helium-3 hold promise for a cleaner fusion process, producing fewer radioactive byproducts. Some scientists speculate that the Moon, after billions of years of exposure to the solar wind, may harbor significant quantities of helium-3. If so, future lunar missions may be tasked not just with exploration but with resource extraction, potentially igniting a new space race for fusion fuel. Long before the first stars, supernovae, or brown dwarfs began forging elements in their nuclear furnaces, there was a time when the universe itself was a fusion reactor. In the seconds after the Big Bang, as matter and energy condensed from the primordial chaos, nuclear fusion occurred on a cosmic scale. Hydrogen nuclei combined to form helium, and trace amounts of lithium and other light elements emerged. This brief but profound epoch, cosmic nucleosynthesis, set the stage for everything that followed, shaping the chemical makeup of the universe and enabling the eventual formation of stars, planets, and life. The pursuit of nuclear fusion represents humanity's attempt to reach back into this ancient, fundamental process and harness it for the future. As scientists continue their efforts to ignite a sustained fusion reaction, they are not merely seeking a new energy source. They are attempting to command the same cosmic fire that has shaped the universe itself. Whether this fire will illuminate a brighter future or serve as a force of destruction remains, as always, in humanity's hands. Big Bang nucleosynthesis, the cosmic alchemy that forged the first elements. If one were the 5th century BCE philosopher Empedocles, they might choose to hurl themselves into a volcano in an attempt to convince their followers of divine status. While this tale is likely myth, Empedocles is better remembered for a more enduring intellectual contribution, his efforts to define the fundamental nature of the universe. In his poem Periphysios, Empedocles introduced the idea that all substances in nature arise from a combination of 4 fundamental roots, a concept later adapted by Plato, who renamed them stoicheia, giving us the term elements. Though these ancient conceptions have long been superseded, they reflect a profound and enduring human desire to uncover the fundamental building blocks of existence. Today, we recognize 118 chemical elements, most of which are arranged within the periodic table in accordance with their shared properties. The heaviest of these elements, however, do not occur naturally in any significant abundance, as they decay too rapidly to persist. The elements that do comprise the observable universe have their origins in the tumultuous life cycles of stars. Through nuclear fusion in stellar cores, stars forge elements up to iron, but elements heavier than iron require more extreme processes, such as the cataclysmic death of a star in a supernova, or the gradual neutron capture within certain types of long-lived stars. Even more violent still is the collision of neutron stars, an event first directly observed in 2017 through gravitational waves detected by LIGO. When 2 neutron stars spiral into one another and merge, the resulting explosion, known as a kilonova, can synthesize and disperse an array of heavy elements. One such event provided direct spectroscopic evidence of strontium, atomic number 38, demonstrating that these cosmic cataclysms contribute to the elemental diversity of the universe. Yet before the first stars were born to forge heavier elements, before supernovae enriched the cosmos with their metallic remnants, there was an even earlier moment of elemental creation, one that unfolded within the first few minutes after the Big Bang itself. The most energetic moment in the history of the universe was its very inception, the Big Bang. In its immediate aftermath, the universe was an incomprehensibly hot and dense sea of fundamental particles, a primordial plasma governed by extreme temperatures and rapid expansion. Within the first microsecond, temperatures were still around 10 trillion degrees Celsius, conditions so intense that individual quarks, the fundamental constituents of protons and neutrons, could not yet bind together. But as the universe expanded, it cooled, eventually allowing quarks to coalesce into hadrons, forming protons and neutrons, the building blocks of atomic nuclei. Of the 6 known types of quarks, 2 dominate the everyday matter of our universe: the up quark and the down quark. The delicate balance of these quarks determines whether a hadron will become a proton or a neutron. Since hydrogen is defined by the presence of a single proton in its nucleus, the moment that protons emerged from the early quark soup was, in effect, the birth of hydrogen, the universe's first element. While neutrons were also initially present in equal abundance to protons, their slightly greater mass made them more susceptible to decay. Within a matter of minutes, neutrons were transforming into protons, electrons, and antineutrinos via beta decay. By the time the universe had cooled sufficiently for nuclear fusion to occur, the neutron-to-proton ratio had dropped to roughly 1:7, an imbalance that would go on to shape the elemental composition of the cosmos. The first step in nucleosynthesis, the process by which atomic nuclei form, was the creation of deuterium, an isotope of hydrogen consisting of one proton and one neutron. Though deuterium could, in theory, have formed immediately, the extreme temperatures of the early universe made its existence tenuous. High-energy photons were so abundant that any newly formed deuterium nuclei were quickly blasted apart. This phase, known as the deuterium bottleneck, temporarily stalled the formation of heavier elements. However, as the universe continued to expand, its temperature gradually fell. Around 300 seconds after the Big Bang, conditions had cooled sufficiently for deuterium to survive intact. At last, the bottleneck broke, and the universe could proceed with further nuclear fusion. Deuterium nuclei combined with protons and neutrons to form helium-3 and subsequently helium-4, the most stable and abundant isotope of helium. This process of Big Bang nucleosynthesis, first theorized in 1948 by Ralph Alpher and his mentor George Gamow, provided a theoretical foundation for understanding the universe's earliest chemistry. In their now famous Alpha Beta Gamma paper, Alpher described how the extreme conditions of the early universe could drive nuclear reactions, transforming hydrogen into helium and setting the stage for all subsequent stellar nucleosynthesis. Yet, while the process of fusion within stars can create a vast array of elements, the primordial Big Bang nucleosynthesis was constrained by a time-sensitive limitation. The universe was expanding and cooling too rapidly to allow the formation of elements heavier than lithium in any significant quantity. By the time the universe was mere minutes old, the temperatures required for fusion had already faded, leaving behind a cosmos primarily composed of hydrogen and helium, with trace amounts of lithium and beryllium. Though the universe was born with only a handful of elements, these primordial constituents laid the groundwork for everything that followed. The hydrogen and helium synthesized in the Big Bang would later coalesce under gravity to form the first stars, igniting nuclear fusion within their cores. These first-generation stars, known as population 3 stars, would burn brightly and die spectacularly, forging heavier elements in their fiery deaths and seeding the cosmos with the raw materials needed for planets, moons, and ultimately, life itself. From the violent chaos of the Big Bang to the intricate nuclear alchemy of stars and supernovae, the history of the universe is written in the language of element formation. The very atoms that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, owe their existence to a chain of cosmic events set into motion nearly 14 billion years ago. And while the details of nucleosynthesis continue to be refined through astrophysical observations and theoretical advancements, one thing remains clear. The universe is, and always has been, an extraordinary factory of creation, assembling the fundamental ingredients of existence from the most extreme and beautiful forces nature has to offer. The cosmic forge, the end of Big Bang nucleosynthesis, and the seeds of a heavier universe. While hydrogen can exist without neutrons, helium cannot. The mutual repulsion of its two positively charged protons would make an isolated helium-2 nucleus an impossibility, as the electromagnetic force would overwhelm the nascent structure before it could even take hold. However, with the presence of just one neutron, the strong nuclear force, the fundamental glue of atomic nuclei, becomes sufficient to overpower this repulsion. The result is helium-3, a stable isotope formed in both the early universe and through modern cosmic processes, such as interactions with high-energy cosmic rays. Left undisturbed, helium-3 is effectively eternal, persisting until the end of time itself. Yet, the most abundant form of helium is not helium-3, but helium-4, an isotope composed of 2 protons and 2 neutrons. Its formation in the primordial universe was dictated by the same forces that govern the fate of all nucleosynthesis. The fusion of deuterium with either helium-3 or tritium provided the primary pathway for helium-4 synthesis, giving rise to the most stable composite nucleus known to physics. In nuclear physics, helium, is described as doubly magic, possessing a symmetrical arrangement of protons and neutrons that makes it exceptionally resistant to decay. This unparalleled stability made helium for the favored outcome of early nucleosynthesis. The universe, much like a great celestial alchemist, displayed a remarkable preference for its creation. Only protium formed in greater abundance. As a result, nearly all available neutrons became locked within helium for nuclei, halting further nuclear progression. This early synthesis was not without constraints. The overall density of matter at the time dictated how much helium could be produced. Had the universe been more compact during Big Bang nucleosynthesis, an even greater fraction of matter would have been funneled into helium, potentially altering the course of cosmic chemistry. In such an alternative scenario, the universe may have contained so much helium, an element chemically inert under normal conditions, that the very foundations of molecular complexity could have been stifled, rendering life as we know it impossible. Astrophysicists estimate that approximately 75% of the universe's baryonic mass after nucleosynthesis was locked in hydrogen, with helium making up the remaining 25%. This fundamental ratio, exclusive of dark matter, neutrinos, and radiation, directly shaped the formation of the earliest stars, the elusive population 3 stars that astronomers continue to seek. Though hydrogen and helium formed the vast majority of matter, they are but 2 of the 118 elements known today. Where, then, did the remaining elements arise? The answer lies in the ticking clock of cosmic time as the universe continued to expand and cool. As nucleosynthesis proceeded, the next element in line was lithium, formed through the capture of additional protons. 2 isotopes emerged, lithium-6 and lithium-7, with the latter dominating in abundance. This was followed by beryllium, formed with 4 protons. However, beryllium-7, the only isotope created in significant quantities, was inherently unstable, decaying into lithium-7 within 53 days. An even greater challenge arose with the fleeting existence of beryllium-8. This isotope disintegrated almost instantaneously, within a billionth of a second, preventing it from serving as a stepping stone to heavier elements. In fact, no isotope composed of precisely 8 hadrons is stable, a fundamental roadblock in nucleosynthesis that prevented the formation of elements beyond lithium in any appreciable amount. At this point, the nuclear forge of the Big Bang began to sputter. With fewer heavy nuclei to facilitate further fusion, and with rapidly decreasing temperatures limiting reaction rates, the creation of elements with 9 or more nucleons became vanishingly rare. If any boron, carbon, nitrogen, or oxygen formed at all, it was in quantities so minuscule that no detectable trace remains in the cosmic record. 20 minutes after the Big Bang, the universe's first great act of creation came to an end. The nuclear fires that had spanned the entire observable cosmos cooled into stillness. At this moment, only 4 elements had been forged, and of those, only 3, hydrogen, helium, and lithium, persisted long enough to witness the birth of the first stars. It would take another 200 million years before conditions allowed for a second wave of element formation. As vast clouds of hydrogen and helium collapsed under the relentless pull of gravity, the first stars ignited in brilliant nuclear fusion. Their immense pressure and temperatures, far beyond anything seen in the early universe, would eventually give rise to heavier elements. But the story of those first stars, their origins, their properties, and their contributions to cosmic evolution remains an open question in modern astrophysics. In our attempt to reconstruct this ancient period of cosmic history, we are left with an unresolved enigma. Observations of the early universe, as inferred through studies of the oldest stars and the cosmic microwave background, suggest a discrepancy between predicted and observed abundances of lithium-7. This inconsistency, known as the cosmological lithium problem, remains one of the most significant outstanding challenges in Big Bang nucleosynthesis. In 2013, astronomers made an impossible measurement. Observations of ancient stars in the Milky Way's halo indicated that their lithium lithium-7 content was significantly lower than theoretical predictions. Despite decades of refinements to nuclear reaction models and observational techniques, this discrepancy persists. Could our understanding of early universe nuclear physics be incomplete? Are there yet unknown processes that deplete lithium in these ancient stellar relics? Or does the answer lie in a deeper, more fundamental revision of the standard model of cosmology itself? The mystery lingers at the very heart of our understanding of the universe's first moments, an unresolved thread in the grand cosmic narrative. And so, as astrophysicists continue their search for population 3 stars and refine their models of nucleosynthesis, they are not merely probing the distant past. They are seeking to answer one of the most fundamental questions of all. How did the universe take shape, and what hidden forces continue to shape it today? The cosmological lithium problem, a scientific enigma at the dawn of time. Among the many celestial bodies that have captured the attention of astronomers, few are as paradoxical as HD 140283, a star that has been observed for over a century. When researchers finally attempted to determine its age with high precision, they were met with an apparent contradiction. This star seemed to be older than the universe itself. Initial calculations placed its age at approximately 14.5 billion years, a staggering result given that the widely accepted age of the universe is 13.8 billion years. Given its antiquity, the star was colloquially named Methuselah, after the biblical figure renowned for his longevity. Naturally, this age paradox pointed not to a flaw in the fundamental chronology of the cosmos, but rather to the limitations and uncertainties inherent in stellar dating techniques. Accounting for systematic errors and refining their models, astronomers subsequently constrained Methuselah's age to approximately 13.66 billion years, comfortably within the universe's timeline. More recent studies published in 2021 suggest it may be even younger, potentially as young as 11.5 billion years. While the exact age remains uncertain, the star's composition provides crucial insights into the early universe. By analyzing Methuselah's chemical makeup, astronomers concluded that it is not a first-generation star, but rather a member of the subsequent population 2 stars, objects that formed after the first stellar generation, known as population 3, had lived and perished. Unlike their predecessors, which contained virtually no elements heavier than helium, population 2 stars like Methuselah exhibit low but non-zero metallicity, approximately 0.1% of the Sun's. Over cosmic time, successive stellar generations enriched the interstellar medium with heavier elements, ultimately giving rise to population 1 stars, such as our Sun, which have metallicities exceeding 1%. The study of population 2 stars is crucial for testing theoretical predictions about the primordial universe. Since the most ancient stars are long gone, their chemical legacy persists as an imprint in stars like Methuselah, allowing astronomers to extrapolate back to the era of Big Bang nucleosynthesis, the period mere minutes after the Big Bang, when the first atomic nuclei formed. However, understanding these relics is not confined to individual stars. Astronomers also examine low-mass dwarf galaxies, which, due to their weak gravitational potential, retain a chemical signature closer to the primordial universe. These galaxies, having experienced relatively little star formation, provide an invaluable laboratory for studying the elemental abundances of the earliest epochs. Observations of ancient stars and low metallicity galaxies have largely confirmed the theoretical predictions of Big Bang nucleosynthesis for hydrogen, including its isotope deuterium, as well as helium-4. However, when it comes to lithium-7, a glaring discrepancy emerges. The observed abundance is only about 1/3 of what theoretical models predict. This puzzling inconsistency is what scientists have termed the primordial or cosmological lithium problem. The predicted abundance of lithium-7 is derived from a fundamental parameter, the photon-to-baryon ratio at the time of Big Bang nucleosynthesis. This ratio, independently confirmed by observations of the cosmic microwave background, should dictate the production of primordial elements with great precision. Yet, Despite the consistency of hydrogen and helium measurements with theoretical expectations, lithium remains anomalously scarce. Scientists have proposed three primary explanations for this enduring enigma: stellar processes and observational biases. One possibility is that the lithium is not actually missing, but rather concealed or destroyed in ways we have yet to fully account for. Stars, particularly old and hot population II stars, are highly efficient at depleting lithium through convective mixing and nuclear fusion processes. Given that astronomers can only observe a star's outer layers, it is possible that significant amounts of lithium are hidden beneath the photosphere. Additionally, uncertainties in temperature measurements can introduce systematic errors in abundance estimates, leading to potential miscalculations of the lithium content. Nuclear physics beyond current models. Another avenue of investigation lies in refining the nuclear physics governing lithium's formation. Lithium, 7, primarily forms via the decay of beryllium, 7. If the nuclear reactions that produce or destroy these isotopes operate slightly differently than current models suggest, it could help resolve the discrepancy. In 2015, a team of researchers reassessed the nuclear pathways of beryllium, 7 formation and decay, yet their findings only deepen the inconsistency between theory and observation. New physics and cosmological implications. The most radical solution posits that our understanding of fundamental physics is incomplete. Theoretical predictions for primordial element abundances rely on our knowledge of the 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear interactions, as well as the properties of elementary particles and the expansion history of the universe. If the early universe contained unknown exotic particles or interactions that altered nuclear reaction rates, this could provide an explanation. Additionally, the influence of dark matter or unknown variations in the early universe's density distribution might have subtly modified the synthesis of lithium. Another intriguing possibility is that our assumptions about the large-scale homogeneity of the cosmos are flawed. Cosmological models assume that the universe is statistically uniform on large scales, meaning that any observer, no matter their location, should infer the same fundamental properties of the universe. However, if our region of the cosmos is slightly underdense compared to the cosmic average, our local measurements could be biased, leading to discrepancies in inferred element abundances. Resolving the cosmological lithium problem remains one of modern astrophysics' great challenges. Future advancements in observational astronomy, particularly with next-generation telescopes capable of probing the chemical signatures of ever more distant and ancient stars, may help refine our understanding. Likewise, improvements in computational models and nuclear reaction measurements could either confirm or refute current theoretical frameworks. Ultimately, this puzzle is more than a mere technical anomaly. It is a potential window into undiscovered physics, the nature of the early universe, and the evolution of matter from the first instance after the Big Bang to the formation of galaxies, stars, and planets. Whether the solution lies in improved measurements, revisions to nuclear physics, or a profound shift in our understanding of cosmology itself, the answer will bring us one step closer to unraveling the mysteries of the cosmos. And so, we continue our journey, seeking to decode the fundamental narrative of our universe, from its fiery birth to the intricate cosmic structure we inhabit today.